Greetings and salutations, magical chemists. Let's talk about Dalton's law of partial pressures, which is the revolutionary idea that if you want the total pressure of a mixture of gases, you just add the partial pressures together. That phrase, partial pressure, just means the part of the total pressure that applies from a singular gas. So let's try an example problem. So we've got a sealed container of helium, hydrogen, and nitrogen, and it's measured to have a pressure of 288 kilopascals. Well, if the partial pressures of helium and hydrogen are 112 kilopascals and 83 kilopascals, what would be the partial pressure of the nitrogen? And yes, I promise this question is just as easy as it looks. But let's go ahead and set this up. You may remember writing a partial pressure for a given gas from our equilibrium of gases, or KP expressions. But really all you do is you put a capital P and then you put a subscript with the elements of the gas. So I have the partial pressure of helium plus the partial pressure of hydrogen plus the partial pressure of nitrogen. And we're remembering, of course, that hydrogen and nitrogen are diatomic. So that means if I want to solve for the partial pressure just of nitrogen, I have to take the total pressure and subtract the two partial pressures I'm given. Well, the total pressure, the pressure of the container, was given to me as 288. And then I'm going to subtract away the two partial pressures I know. And what remains must be the partial pressure of the nitrogen gas. In this case, 93 kilopascals. And you're done. Now, there's a very useful application of Dalton's law you might remember from your lab in pre-AP that we did last year. But it is the collection of gas over water. This technique is used if you want to know the quantity, the volume specifically, of gas you are collecting. You have to use a rigid container. But if you have a rigid container and it's currently full of air, it's really hard to tell how much of it is full of whatever gas you're collecting. So what we do instead is we fill the container of water and then you bubble in the gas that you're collecting. And then that gas, as it fills up the container, is basically pushing the water down. The trick is knowing when to stop. You have to stop collecting gas when the water levels inside of your collection container and outside of your collection container are equal, because that's when the pressure inside the container is equal to the atmospheric pressure outside the container, because it's really hard to measure the pressure in the container, but it's really easy to measure just, say, room pressure or atmospheric pressure. Now, this technique is super useful, but you have to recognize that the gases you've collected is not pure. It is a mixture. I mean, otherwise it wouldn't be Dalton's law, right? They actually will call it the quote-unquote wet gas, because as it's bubbling through the water, some of that water is evaporating into water vapor. So in the collection vessel, you have not just the gas you wanted, but you also have gaseous water. And of course, the gaseous water, or water vapor, exerts a pressure, like any other gas. So we'll usually do a calculation to find what's called the dry gas pressure, aka the pressure of the gas without any water mixed in. Well, we're just using Dalton's law, and you're going to subtract the vapor pressure of water at the temperature that you collected your gas, and you subtract it from the barometric, or atmospheric pressure, which of course is just a measure of your total pressure. So you'll notice this is just a variation on Dalton's law. Whoops. So you have a total pressure equal to the partial pressures of two separate gases. Now, a lot of times in a Dalton's law problem, they're going to tell you the vapor pressure of water. They'll be like, oh, the vapor pressure of water at 20 degrees Celsius is blah. But they won't always. And honestly, with Mastering Chem, you never know. So here is a table of water vapor pressure that is looking at basically all the different temperatures versus the vapor pressure of water in mmHg at that particular temperature. So you can use this table to look up the partial pressure of water at a given temperature as needed. All right, let's try a practice problem. It will be delicious. Okay, so in this experiment, we're decomposing potassium chlorate by heating it. And when you do that, oxygen gas is produced as part of the decomposition. So we're collecting the oxygen gas by, bubbling it through water, fancy that, and collecting it in the given vessel. So we want to calculate the partial pressure of oxygen that was collected, otherwise known as the dry pressure of oxygen. So I think you should totally try this problem. And when you're ready to check your answer, unpause the video. Okay, first you're recognizing that the total pressure that's measured, in this case our barometric pressure, is going to be a combination of the partial pressures of oxygen and water. So all we need to do is subtract the partial pressure of water from the total to get the partial pressure of oxygen. Now, of course, they didn't actually give you the partial pressure of water, so that's why we have that convenient table. Since this experiment was conducted at 22 degrees Celsius, the partial pressure of water is 19.8 mmHg, or, torr. Now, mathematically, that gives you a final partial pressure of oxygen of 734.2 torr, but sig figs. Remember, sig figs of subtraction are by place value. And since the first number that we're using, our total pressure, is only significant to the ones place value, we have to round our answer to the ones place value. So our final answer is just 734 torr. Okay, in the second question, they want to know the mass of our potassium chlorate that was decomposed. But I don't have any given information like moles or anything really about the potassium chlorate, but I do have information about the oxygen being produced. So this is a stoichiometry problem. I know you're as thrilled as I am. However, before we can actually do the stoichiometry, we need to calculate the number of moles of oxygen, and this is not happening at STP, because that would be no fun. So first we're going to use PivNert to calculate the number of moles of oxygen gas, and then we can do stoichiometry to find out the mass of the potassium chlorate. So rearranging PivNert, N, or number of moles, is of course PV divided by RT, so then we just need to plug in our variables. We're using the partial pressure of oxygen that we calculated in part A, and then they gave us the volume in the problem. And because we're in torr, we're using the 62.36 value of R. And of course, we are converting to Kelvin. And when you plug this in, it gives you a pretty tiny number of moles. So now that we have the moles of O2, you can do delicious stoichiometry in all of its glories to find the mass of potassium chlorate. You should try that, just to make sure that stoichiometry is still your friend. And when you are ready to check the answer, unpause the video. So first we use our mole ratio from the balanced equation, and then of course the molar mass of potassium chlorate to convert to grams. And so when you plug in all the numbers, you discover you should have 2.12 grams of potassium chlorate that were decomposed in this experiment. All right, last but not least, we want to know the volume of the dry oxygen gas, but at STP, of course, different temperature and pressure conditions. Well, luckily, we already have calculated the number of moles of oxygen gas, so it's easy enough to plug into PivNert under new conditions and calculate the volume at STP. Volume, of course, is NERT divided by P, so then we just plug in our variables. This time, because we're working at STP, which is commonly given in atmospheres, we're using the tiny value of R, the 0.08206. But you don't have to. You could convert it to torr, as long as you're using the correct pressure for STP. So when you plug all the numbers in, you'll get 0.581 liters of oxygen gas. This is our dry oxygen at standard temperature and pressure. The moral of the story is that this problem, which was nominally Dalton's law, which it was, also involved lots of other mathy things. So many times Dalton's laws is used in gas laws in combination with other gas laws. Yum! Speaking of other gas laws, there is one more thing we need to look at, and then we will be done with this video. Now, we already know, of course, Dalton's law, that many gas samples aren't pure, but instead are mixtures of different gases. However, there are some times when you can actually treat all of the mixture together as just a single gas, one gas, and do the math that way. If you calculate the total number of moles of all the gases, you can plug that into PivNert and calculate the total pressure of your container. So there's nothing new about this math. It's just recognizing that this is a thing that can be done. Now, speaking of things that can be done and mathy math, let's look at something known as mole fractions. Now, mole fractions we do not commonly discuss in pre-AP, but they're actually pretty straightforward. It's another way of finding the partial pressure of a gas by looking at the number of moles of your component in a mixture as a ratio to the total number of moles. And this is given to you on the formula chart, so it's weird. It's like represented with an X or whatever, but you don't have to worry about it. It's given to you, so this is not something you have to memorize. So it's literally a ratio, how many moles of your gas divided by the total number of moles in your container. And you can use the mole fraction to determine the partial pressure of a component. All you do to find the partial pressure of, say, gas A, is you take the total pressure and you multiply it times the mole fraction. And that's it, short and sweet. And that equation is on the formula chart as well. Okay, let's try a couple practice problems and we'll be good to go. So in the first problem, it gives you the mole fraction of nitrogen in the air. There's lots of nitrogen in the air, right? That's a pretty high mole fraction, 0.78. So we're going to calculate the partial pressure of nitrogen in the air if the atmospheric pressure is standard pressure, 760 torr. Well, this is very short and sweet. Remember, to find the partial pressure, you just take the total pressure times the mole fraction. That's it. So 760 times 0.7808, well, that gives you about 78% of the total pressure. Well, that's the pressure due to nitrogen, which ends up being 593 torr. Okay, let's look at another example problem. In this case, you're combining two different containers of gases. So flask A is helium, flask B is argon, and we want to combine them both into, now when it says previously evacuated, that just means there's no gas inside until they added the new ones. So we want to calculate the new pressure of our new flask. Well, okay, there's two ways of looking at this problem. If this final flask were the same volume as the initial ones, then this would be a super easy calculation. So let's look at what would happen if we had instead combined it into a 1 liter flask. Well, you'd be adding the partial pressures, right? So you'd get the 1 atmosphere from the first flask plus the 3 atmospheres from the second flask. So hopefully it should be no surprise, you would have a pressure of 4 atmospheres in that new flask. But that's a 1 liter flask. In the flask that we were actually given, we're taking that 4 atmospheres, but now we're basically giving it 4 times as much space. So we have to take our 4 atmospheres and divide it by 4. Because remember, pressure and volume have an inverse relationship. Luckily, 4 divided by 4 is a very easy calculation, right? This is how we get our 1 atmosphere of pressure. And that's it. The math is short and sweet. You just can't forget to take into account if the flask size changes. All right, we're done. That was a crazy whirlwind review of gas laws. So I will see you in class for more fun and excitement.